Here are some notes about counting. This might seem exciting, right? Counting back to elementary school. Well, we're going to do a little bit more involved counting, not like counting the number of apples on the table. More like number of ways to arrange things. So here's my favorite example. Let's say you have 2 shirts, 3 pairs of pants, and 5 hats. How many possible outfits are there? Assuming that you're going to wear 1 shirt, 1 pair of pants, and 1 hat, and that consists of 1 outfit. You might have seen questions like this before, especially at restaurants, when they're like, oh, pick any of these 3 appetizers, 5 entrees, and 2 desserts, and there's tons of combinations. So let's see how we can figure out how many outfits there are. One way of thinking about this is by drawing a tree diagram. Let's say you start with shirt 1. There's 2 shirts, so let's say you have 1 of the shirts. For that 1 shirt, you could wear any of your 3 pairs of pants. For each of those 3 pairs of pants, you could put on 1 of the 5 hats. So these 5 lines are representing the 5 choices you have for hats. The shirt 2 diagram would look the same. 3 possible pants, and then 5 possible 1, 2, 3, 4, 5 hats for each one. So how many kind of endpoints are there? You could think of for each shirt, there's 3 pairs of pants. For each pair of pants, there's 5 hats. So the number of outfits is actually just 2 multiplied by 3 multiplied by 5. We're multiplying all of our options at each sort of juncture. And that gives us, what, 30 possible outfits. So this is kind of the simplest type of counting problem. This is using something called the fundamental counting principle. And all that principle says is that if you're given a certain number of options within each category, all you do is you'd multiply the number of options within each category together to get your total number of, outfits or meals or number of ways to get from point A to point B, whatever that is. But sometimes we're not interested in categorical data. What if we had a different type of question? What if we wanted to know how many groups of 3 people are possible out of a total of 10 people? So maybe there's 10 people in an office and you want like a 3-person committee. Before we answer this question, I want to also write down another question. How many 3-person lineups are possible out of 10 people? So here we're still picking 3 people, but this time we're lining them up in an order. So if you imagine 10 people, A, B, C, D, E, F, G, H, I, J, those are the names of the people. In this first example, a group of ABC is the same as the group BCA. It's the same people, it's the same group, it's the same committee. So the order in which we would line up the people does not matter. For the second example, since I'm lining them up in it, the only reason I know that is because it said so in the question. If I take ABC, that is not the same lineup as BCA. So in this case, order does matter. So in each case, we're selecting a group of 3 out of a group of 10, but in the first case, order doesn't make a difference, and the second example, order does make a difference. We have names for those types of choosing. This first one is called a combination. A combination is when you've selected a group where order does not matter. The second type is known as a permutation, where you've selected a group, but order does matter. And we actually have a formula for a combination of selecting R things out of N things, and for a permutation of selecting R things out of N things. So let's look at our combination formula. If you're choosing R things out of N things, the way you would write that is NCR. Notice the C is big. It's in the middle, and the n and the r are kind of the same size, and that's just a notation thing. So in this case, we are interested in, we have 10 people, and we're choosing 3 of them at a time. That's how we would write that. Another way that you'd actually see this is like this. Sometimes you'll see that. It's n kind of over r. There's no, it's not a fraction or anything like that. It's just kind of n written above an r in these big parentheses. That's just another notation. And the formula is n factorial over r factorial times the quantity n minus r factorial. So for our specific example, 10 factorial over 3 factorial times 10 minus 3 factorial, which is 7 factorial. And, I could maybe reduce this fraction a little bit. If you were to enter this in a calculator, don't forget you would need to put parentheses around each factor in the denominator, around both of them, that is, to make sure you're dividing by the quantity 3 factorial, 7 factorial. And I think that's equal to 120 ways. Let's look at the permutation problem. We would write this, well, instead of a C, you might have guessed it, we're going to use a P. We're taking R things out of N things, but this time the order within that group of R things does make a difference. So in this case, we are taking 10P3. And our formula here, it's actually a little bit simpler. N factorial over the quantity N minus R factorial. So in our specific example, it would be 10 factorial over 7 factorial. And before you even calculate this, you might ask yourself, is this going to be a larger number or a smaller number than 10C3? And if you look at the fractions, the numerators are the same. They're both 10 factorial. But the denominator is smaller in our permutation example because it doesn't have that 3 factorial multiplied by it. So since our denominator is smaller, we're dividing the same thing by something smaller. That means our answer will be larger. And in fact, it is. I think this is 720 ways. And that should make sense. You're counting more things because ABC is not the same as BCA. So we have to count those as separate things. There's going to be more total things. Your calculator does have a button for these. If you look in, I believe it is Math and then PRB. And then choices 2 and 3, I think, are NCR and NPR. And you just have to type like 10 and then NCR 3. You'd have to type the N value first before you select that. So you can play around with those on the calculator. Let's just do actually one other interesting example. How many ways, what is the number of ways to line up 15 people? So what if I'm like not selecting a certain group out of them? What if I just want to line them all up? Well, you could still think of this, order definitely makes a difference. You could still think of this as a permutation. We have 15 things, and we're taking all 15, 15P15, to line them up in a specific order. By our formula, that would be 15 factorial over 15 minus 15 factorial, which is 0 factorial. But remember, 0 factorial is defined to be 1. So this is the same as just 15 factorial, which is some large number. So we can think of just lining a bunch of things up also as permutations. So here's another example, though. Let's kind of switch gears a little bit. Out of 10 people, we need a number of ways to form a 3-person group and a 5-person group. Okay, so instead of just saying, one specific group, like a group of 3 out of 10 or a group of 5 out of 10, now we're taking 2 groups at the same time. And when we have an example like this, we can't use permutations or combinations because they're really only for selecting one group at a time. And now we're choosing more than one group at a time. So you can think of the situation as like you're in an office and we need a party planning committee of 3 people, and then we need a budget committee of 5 people, and you're not allowed to be in the same committee at the same time. So that's kind of a real-world example of this. We can use something called the fundamental labeling principle here, and this is another handy way of counting things. If we can give every item in our group a label, then we can use this principle. And here's what it would look like. The total number of items factorial would go in the numerator. Total number of people is 10. And then the number of items with each label factorial goes in the bottom. So there's a 3-person group. You could be in the 3-person group. There's 3 of them. So we're going to write 3 factorial. You could be in the 5-person group. There's 5 of them. I'm going to write 5 factorial. But there's another hidden label. What if you're not in either group? Well, then you're one of those 2 people that's not in a group. So each one of these pieces in the denominator is representing a label of a person. These are the people in one of the groups. These are the people in the other group. And these are the sad people that are in no group whatsoever. So we could then evaluate this. I think it ends up being like 2,520. I'm not sure. Something like that. Sounds about right. But this is a handy way of counting things if you're picking more than one group at a time. Let's do one more example. How about the number of ways to rearrange the letters in the word cheese? Now, be careful, because if we were just to switch the place of these 2 E's, the word would not look any different. And that's what makes this problem more complicated than just, rearranging the letters in cat or something like that. When you have repeated letters, if the E and the E switch spots, or even maybe this E and another E switch spots, it looks the same, so we can't double count those. We can use the fundamental labeling principle here. We can give each letter a label. Let's see, what labels would there be? There would be the label C. There's only one thing that has that label. There would be the label H. There's only one thing that has that label. There would be the label E. There are 3 things that have that label. And there would be the label S. There's only one thing that has that label. And we've taken care of all the letters. So using our labeling principle, we put the total number of items on the numerator, factorial, so that would be 6 factorial. There are 6 total letters. And then 1 factorial for the C's, 1 factorial for the H's, 3 factorial for the E's, and 1 factorial for the S's. Of course, 1 factorial is just 1, so that's the same as 6 factorial over 3 factorial, which ends up just being 6 times 5 times 4, which is, 120. So it's handy for things like that. And we can even go back to those examples we saw on the previous page with the permutation combination, just choosing a 3-person group. Really the same thing. If you were to use the fundamental labeling principle there, we would get the same answer. 10 people, 3 people in a group, 7 people not in a group. That's where order did not make a difference. 10 people in a group, for the permutation example where we were lining them up, 1 person has to be first, 1 person has to be second, 1 person has to be third in the lineup, and then 7 people are not in the group at all. So that's another way of thinking about those same problems using the fundamental labeling principle. And notice we ended up with the exact same expressions we did on the previous page. So most counting problems can be solved using one or more of these concepts: the counting principle, the labeling principle, permutations, combinations, maybe mixing them together in some way. But counting can be fun. Good luck.